Chapter 2, Section 2.4, Derivatives of Trigonometric Functions. Derivatives of trigonometric functions. In particular, it is important to remember that when we talk about the function f defined for all real numbers x by fx equals sine of x, it is understood that sine x means sine of the angle whose radian measure is x. In other words, you are using radian units for x, okay? A similar convention holds for the other trigonometric functions, cosine, tan, cosecant, secant, and cotan. All of the trigonometric functions are continuous at every number in their domains. All right. Now, if you remember, if you sketch the graph of sine, you notice, okay, sine starts off at 0, climbs to 1 at pi over 2, climbs down, and so on. Whereas cosine starts at 0, at 1 and climbs down. Anyhow, we'll come to derivative in a minute. Okay, if you draw the curve, f prime x is slope of the tangent. Okay, so use that argument for sine. You see, at pi over 2, slope of the tangent is 0. So at pi over 2, derivative is 0. At 0, slope looks like positive 1. At 0, slope is positive 1. So f prime, the derivative function, looks remarkably same as cosine curve, okay, which is what we are going to aim for. Now, let's try to confirm our guess that if function is sine x, then f prime x is cosine x. Well, we are using definition of derivative. F prime x is limit h approaching 0, f of x plus h minus fx over h. F is sine, all right. Now notice you are going to use the sum angle formula for sine. Sine x cosine h plus cosine x sine h minus sine x, the whole over h. Now move that sine x with the negative in between. Move this aside and don't forget to distribute the h. That's what we have done here. Here notice sine x is common. Sine x is common. What's left over is cosine h minus 1 over h plus cosine x sine h over h. When you take limit h approaching 0, this quantity is 0. This limit is 0. This limit is 1. So all you're left with is cosine x. All right. In other words, so the limit sine h over h is not so obvious. We have made the guess on basis of numerical and graphical evidence that limit theta approaching 0, sine theta over theta is 1. Now here is a small proof. Assume that theta lies between 0 and pi over 2, that is 0 and 90 degrees. That is, theta is an acute angle. So if theta is an acute angle, well, let's draw a right angle triangle. All right. Now use radius 1 and draw an arc which meets at A. Okay. What does that mean? OA is 1, OB is 1. BC is drawn perpendicular to OA. By the definition of radian measure, we have arc length AB equals theta, because arc length is radius times theta. Radius is 1, so arc length is theta. Also note BC is OB times sine theta, but OB is 1. So BC is sine theta. Length BC is sine theta. All right. From the diagram we see that BC, length BC is less than length AB, which is less than arc AB. So let's go back. BC, AB, and AB. BC is less than length AB. Why? Because this is a right angle triangle. AB is the hypotenuse. So hypotenuse is indeed longer than either of those sides. In particular, AB is bigger, has length bigger than BC. On the other hand, this arc is subtended away, so that arc is longer than AB. So that's what we are saying, right? In other words, this is sine theta and this is theta. So divide both sides by theta, knowing that theta is positive, you get less than 1. Okay. Now, let the tangent lines at AB and A and B intersect at E. So you have drawn tangent lines here and here. Okay. You can see from this figure that the circumference of the circle is smaller than the length of the circumscribed polygon. Okay, so this polygon will have a circumference bigger than the circumference of the circle. In other words, the arc AB is less than AE plus EB. All right, arc is less than AE plus EB. AE plus ED. What is this ED? Go back to the triangle. So that is AE plus EB. Look at that, right? That's another right triangle. So EB is smaller than ED because ED is the hypotenuse over here. All right. So that's what we are using. But what is ED? ED is OA times tan theta, right? What is ED? OA times AD is, hold on, what was the question? Yeah, these two together is AD, which is correct, right? These two together is AD, and AD is, so tan theta is AD over here, so AD is tan theta. All right, so that's AD is tan theta. So you have theta less than tan theta. Tan theta is sine over cosine. All right. So multiply by cosine and divide by theta. Why can you do that? Because for this 0 to pi over 2, cosine is positive. Theta is positive. So you can do this maintaining inequality. So you now have cosine theta is less than sine theta over theta, which is indeed, in fact, less than 1, which is what we saw earlier. All right. Now it's time to use squeeze theorem. Limit of constant function is itself. Limit cosine as theta goes to 0 is 1. So both these ends limit to 1. Therefore, sine theta over theta, when theta is coming to 0 from the right hand side. Why? Because theta is positive. So that's 1. On the other hand, sine theta over theta is an even function. So the left limit will also be the same. Therefore, we have limit theta approaching 0, sine theta over theta is 1, which is what was used to find the derivative of sine. All right. So with that, we can now use, we need to figure out cosine theta minus 1. Take its conjugate, multiply numerator and denominator. That gets me difference of squares, right? Cosine squared minus 1 is negative sine squared. So now distribute this. You see, there was a theta over here. I believe that's missing here in the typo. Anyhow, 1 of the sine theta, you take that theta as the denominator. The other sine theta remains above. That negative is over here, and there you go. This gives me 1, and this gives me 0 upstairs and 1 plus 1, 2 downstairs. So overall, this limit is 0, which also got used in our work. So this is 0 and this is 1. That's what we needed. All right. So with all this information, you know that the derivative of sine function is cosine function. All right. Derivative of sine is cosine. All right. We'll come to the rest of the slides in our next video.